All right. So it's a great pleasure for me to introduce Suchir Naik. So Suchir is now at Packaging Corporation of America. He's been a student at Purdue University Fort Wayne. He's an expert on many aspects of computer science, machine learning, and predictive modeling. He has worked in relations to the Indiana Mine grant for a corporate partner project and laboratory data science, and it's done great work, and it's a great pleasure for me to hear what he has to say about breast cancer treatment expert systems. So please take the stage.
Thank you so much, Professor. So this is a very recent project of mine, something which I it's going to get published. It's been selected and I finished my presentation just last month, and it's probably going to get published this month, in the month of April. This is a continuation of my previous project on breast cancer. So how I've divided, so this is something which I've done. I've divided my projects into phases. The first phase of my project, which has already been published, the first part was a recommendation system which I built. That was a forward chaining recommendation system, which gives out recommendations based on user inputs that has been integrated with Chat GPT. The second part of the system was to kind of add on to that recommendation system, which is the detection side of it. That is, it takes in mammogram images and then gives a classification of whether the tumor was benign or malignant. And then I have a phase 3, which I'm currently working on now, is basically I'm fine-tuning my own large language model. I'm using a llama model and fine-tuning it on my own using LoRa and Clora. These are the new fine-tuning techniques which got released in the year of 2023. I'm trying to create my own large language model on medical data and then integrate my recommendation system, forward chaining inference system into that large language model. So that's the complete, I think, phase which I'd set out, or the expectation which I'd set out for myself. But I wasn't able to complete the whole thing during my study at Purdue Fort Wayne. But yes, I was able to finish phase 2, which is the detection side of it. So just to give you a very brief introduction and why I picked up this project on the breast cancer expert system, which is the complete part, but this validation, which I'm going to be the detection part, which I'm going to be talking about now, is just a phase 2 of my project. But the complete, why I picked up this complete project and the motivation behind it was because back in India, I had some experience with breast cancer patients and visiting doctors. And what I learned is back in India, there are a lot of underprivileged people who don't have access to personalized breast cancer treatment. A lot of times they do get access to government hospitals and doctors, but these are not personalized, and they don't get to spend a lot of time with the doctors and ask a lot of questions. So my first motivation was to develop that project, which is the recommendation systems, to give more of a personalized access to breast cancer. It was not to replace doctors, but to help underprivileged people get access to personalized breast cancer treatment. And the second part, which is my detection part, was to basically classify these tumors so that it acts like an aid for doctors, which helps them also kind of validate whether the recommendation which they've given is correct or not, as well as in some areas where like India or also in Africa, a lot of patients do visit India from Africa, and what they don't have is access to these treatments and doctors, as well as access to doctors who can classify mammogram images. So that was another aspect which I wanted to create a detection system to my recommendation system, which is why I built this detection system, which was basically I was comparing vision transformers, I was comparing CNNs, I was comparing traditional machine learning algorithms to see how they compare against each other. So that's the basis of my introduction, which is why I picked up this project, as well as some introduction to breast cancer treatment. So this is the motivation. And these are the two related works which I referred to. It was Agarwal and Zahoor. These were the two major papers which I picked up. These were basically hybrid approaches where they used classic CNN models like the VGG16 or the mobile net V2. And then they also had their custom dense layer, which they fed those CNNs to basically classify the mammogram image. So I wanted to go a step further. What I saw was vision transformers was something which was not researched a lot when I picked up this research. There were very few papers on vision transformers. So I wanted to expand this concept of basically what they had used. They had used CNNs and then trained those CNNs for classification. What I did was I picked up vision transformers to basically do my classification, which is again more like an extension of the classic transformer models which you have for NLP related tasks. I basically kind of extended that to the vision side, which is to classify breast cancer images. And these were the two papers which I majorly refer to basically get more of the literature for building my project. So I'll quickly take us through the data pre-processing which I did, and then talk about more about the vision transformer. My project was not very concentrated towards the CNNs and machine learning models, but it was more on the vision transformer. I built my own custom vision transformer architecture. I wouldn't say custom, but it was using the VIT bit 16 model, and then I created parts to it, that is unfroze certain parts and then created my own dense layer to kind of create more of a custom architecture for myself for classifying these images. So I'll talk more about the VIT transformer, but I'll also go through the complete scope of the project. So the data set, what I used was the digital database for screening mammography. This was the DDSM data set which I used. And the composition of images which I used was 2,000 images. 1,000 were benign and 1,000 were malignant. One thing I'd like to mention here is the images is not, the images I used to train the model is not very exhaustive. That's something which I'd like to address. And that's something which I will go forward, because this was more of an exploratory phase where I was trying to see how the different models perform, and then use a larger data set to train the best performers. So that's what my motivation was for this project. So I used a smaller image size to test all of the different models, and going forward I'll be training the model on a larger data set, which is my vision transformer, which performed the best. I'll be training it on a larger data set, but right now the data composition which I used was 2,000 images. So some of the pre-processing steps which I did was I initially took the images, I converted them into a 224/224 pixel size, and then also converted them into an RGB format, which is red, green, or blue, which created a resolution of 224/224/3. And after doing this, what I did was I did a normalization. That is, I divided the pixels by 255 because each pixel value goes from 0 to 255 for RGB value. I normalized that so that because it helps the model in learning the image features better when you normalize the input size. So that I did a normalization, and after doing the normalization, I basically did a one-hot encoding of the benign and malignant images. And why I did the one-hot encoding is because in the end we have a softmax layer which takes the input in the form of a one-hot encoding. It does not take it in a single column, but you need different two columns or a one-hot encoding for inputting it into the softmax layer, which is why I did the one-hot encoding. And after that, we did basically a splitting of the data, which was the train, validation, and the test. The train was 60%, validation was 20%, which we used in the back propagation to train the model. And then we finally did the accuracy testing on 20% of the unseen data set, which was the test data set. And then I also used traditional ML models. For the ML models, I flattened the images because that's how the ML models take it. But I won't go into a lot of depth of the ML models. More of the talk will be on the vision transformer side of it. So that was the basic pre-processing which we did. So going on to the model architecture, how I basically use this vision transformer is I use the VIT bit 16 model. So this VIT bit 16 model has basically 12 layers in it. It has a 12 layers in it. And apart from that, I used another set of custom CNNs as well as pre-trained CNNs to basically compare against how they were doing, how these models were performing against the vision transformers. So to give you a very general idea of what I did, across all of these different models is for the vision transformers, what I did was I did a model fine tuning plus I did a transfer learning. And then I use this vision transformer as a feature extractor and then fed it to my own dense layer to basically train the model and then give the output. In the case of the pre-trained CNNs, what I did in the pre-trained CNNs is I did not do any fine tuning here. I just used them as feature extractors, basically pass the input images to these pre-trained CNNs and then use them as feature extractors to extract the array and then feed that to a dense layer, which I used for the training and then give the output. That's how I did the pre-trained CNNs. And then I also built my own custom 3-layer convolutional network just to see how my custom CNN was performing against the other VITs. And then for that I used a 3 convolutional layer of 3264 and 128 filters to basically build my custom CNN. So this was how I basically did the comparison. And only in the vision transformer is where I did the fine tuning. I did not do any fine tuning in the pre-trained CNN since my concentration was more around the vision transformer. And then, of course, I also trained the model on a random forest classifier as well as a support vector classifier just to see how these models were performing compared to my my vision transformer. So this was the complete model evaluation. The VIT model is got an accuracy of 96%. And we also had certain models which had a higher accuracy. The VGG16 had 98% accuracy. The DenseNet had 98. It was slightly more than the VIT model. But why I would select the VIT model here is you can see that it is able to generalize better. I wouldn't say that the VGG16 or the DenseNets are overfitting because against the validation accuracy, you can see that the accuracy has not dropped a lot for the test accuracy. It's not dropped a lot. But I would say that the vision transformer is more of a generic model. The test accuracy is not too high. It's not very high, but it's somewhere, it's a good test accuracy which I've got. And it's not also dropped a lot compared to the validation accuracy, which is why I feel that the vision transformer is actually doing a really good job against classifying these mammogram images. And I want to basically dig deeper and see how it does when I expand the data set to a larger data set and how the VIT model performs against these other models. So that's something which is a future scope, but right now the VIT model, it got an accuracy of 96%. So I'll quickly talk about what happened in the VIT model. I'll not go into the other models. So I'll talk about what I did with the vision transformer. So how I designed the vision transformer is after doing all of the data pre-processing, I fed the images as a NumPy array to the vision transformer. And what the vision transformer does is it does its own image patching conversion of the NumPy array into the respective input format which is required for the vision transformer, and then it does the training. So in this training process, what I did was I first looked at 3 variants. One where I freeze all of the layers of the vision transformer. What this is a pure feature extractor. I'm not doing any fine tuning when I froze all the layers. That is, it is just using the pre-trained features which it had. It's only performing the providing the features based out of all the learning which it had done previously. The other one, what I'm doing is I'm unfreezing all of the layers. When I unfreeze all of the layers, what I'm doing is I'm training it from scratch, which is why you can see that the accuracy dropped considerably. And the last one, which is the best output which I got, is I unfroze the last 2 layers, but kept the first 10 layers of the vision transformer frozen. And the reason why I did this was based on a lot of the literature survey which I had done. What I learned was most of the generic feature learning happens in the first 8 to 10 layers. That's where the generic feature learning happens, and most of the specific feature learning happens in the last couple of layers, which is why the VIT bit 16 model, which I had initially basically which I had used, was trained on the ImageNet dataset. So it had already learned a lot of features on which it was trained on the ImageNet dataset. So I did not have to unfreeze all of the layers. So I could keep all of the learning which it had done in the first 10 layers, but the last 2 layers is where I unfroze it. And I basically fine-tuned it on the data set, which is the breast cancer data set, which I'd used for classifying the benign and malignant images. And after that, what I did was, in the actual vision transformer, it actually has a classification layer. So I made that classification layer as false because we don't want it to classify ImageNet dataset, but we want to classify it on our custom dataset. So I removed the last layer, which was the classification layer, and I used all of these features and extracted those features and fed that into a dense layer, which I had created. So I created my own dense layer, which I had created, and I used the ReLU activation function. And this was basically the dense layer which I had created, and then I fed that into a softmax layer. A softmax layer is where the classification happens. So apart from the vision transformer, if you look at it at a more broader perspective, you have the vision transformer, which is used for extracting the features. It extracts the features as a NumPy array, and then you flatten that into a 1D dimension and feed that into a dense layer. After that, you pass those trained features which it has learned into a softmax layer. So the softmax layer basically does the classification. It does the classification of whether it was benign or malignant, and then it compares it against the validation data set. It compares that against the validation data set, and it tries to see and match if the classification was correct or not. And based on that, I also have a cross entropy loss function, which basically does the back propagation side of it. It does the back propagation side of it, and then it basically learns that I created 10 epochs, so it does this complete steps over 10 epochs. It does it 10 times to basically get the classification right, and finally it gives out the classification after the 10th epoch. So that's basically how I created my VIT layer. I know it sounds a lot, but if you visualize it, the VIT is basically the feature extractor. The dense layer is where the training happens, and the softmax layer is where the classification happens. And all of this is done through a back propagation, and I use the cross entropy loss function to basically for the learning, and for basically the weight updation, I use the Adam optimizer. So these were the two optimizers which I used. So this is basically the complete picture of how I created the vision transformer. And of course, in the vision transformer itself, the last two layers were unfrozen for it to basically learn on that specific custom data set which we had, after which it did the feature extraction and pushed it to the dense layer. So this is how the complete architecture is what I designed for the vision transformer. And the best accuracy which I got was 96.6% for the vision transformer for the last two layers which were unfrozen. So this was the complete crux of how I designed that architecture. And yes, I of course also deployed this into an Azure ML service. So I built a pipeline and deployed the PKL file, and you also can create a real-time endpoint on Azure ML service, which I linked it with a small, very basic UI website which I had created. The website was basically classifying the images which I created. So it would take in an image, and then it would send that to the API. The API would classify the image and send that back, and that would be shown as the output for the website. So that's how I envisioned it for basically the underprivileged people who don't have access. They could just upload their mammogram images and then get back the classification from the model which is hosted at the backend. And this was the simple architecture which I used for Azure. I used the Azure student service. This service has, of course, been discontinued because I could not maintain it. I maintained it for approximately about 2 months, but now it's been discontinued because it started charging me. So I discontinued it after some time. But this was the basic system architecture which I had used for basically building the pipelines and deploying the model. And moving ahead, some of the future works I have is, of course, I want to explore the traditional ML algorithms more. I had some issues with GPUs, etc., but I won't go into too much of it because my main concentration was around the VIT model. I, of course, have to expand the data set. The data set right now was more for me to explore and see how the models were performing, but now I have to basically expand the data set and as well as invest some money into getting some GPUs on the cloud platform. Probably Google Colab is something which I'm looking at to train these models. Something else which I want to look into is possibly quantum computing, how quantum computing works for training these models. That's a field which I want to get into and see how ML algorithms work on quantum computing. I also know that there's a quantum computing lab which has recently started up at Purdue Fort Wayne. So I want to see if I could probably get in touch with the professor there and see if I could explore how the models perform on their quantum computers. Yes, one other important aspect of this complete project is the clinical validation, explainability and the clinical validation. That's something which I'm thinking of in the future. Also, apart from doing this testing and validation on the model side, I also want to get into the clinical validation side of it and see how this model performs in a real world aspect and see how they perform on patients. More like a testing scenario is something I want to do in the future, and possibly get an FDA approval if that is possible. Once I have trained my model on the larger data set, I want to do a clinical validation and also possibly see if I can get an FDA approval. That's something I'm aiming for, but that's very much in the later phases of my project once I've completed phase 3 and phase 4 of my project. So that's something I'm aiming for in the future. And yes, the conclusion is basically the VITR model achieved this accuracy, and my plan ahead is to train it on a larger data set and see how the model performs. Since I chose this model because I feel like it's better at generalizing. So even if I push this onto a larger data set, I feel like I would probably get the same accuracy, around the same accuracy. So I want to push this to a larger data set and see how it performs. That's something I'm looking at in the future. But yes, right now I feel that the VIT model was performing considerably well, and I want to take it forward and possibly see how it performs on the larger data set. And those are the next steps for the project. And that concludes most of what I've done for phase 2 of my project, which is the detection side of it. Thank you so much for listening, Professor.
Okay, so thank Suchir for the great presentation. Maybe I just have one question. So at the beginning you mentioned data set, right? You had 1,000 images per class. So were those images of all of different people?
Yeah, they were all of different people, not the same person.
Yeah. So you had one image per person, right?
Yes.
How was that image chosen?
I did a random selection of 1,000 images from the complete data set. The data set has approximately, I think, around 10,000 images, but I chose randomly 1,000 images.
So were they in which, because they might scan a different a different depth, right? I don't know what to call it. They can scan a different different ways, right? So were they scan all at a particular position, or were they at different positions?
Oh, they were all at different positions. But again, if I go back to this data set, so there are different data sets. Apart from the DDSM, there's also a data set called as the in-breast data set, and there's also another data set, famously used data set. So the DDSM data set is, of course, it's scanned across different angles. It's not at the same angle, different angles. But the DDSM data set and the in-breast data set use different machines again. So that's another aspect to take into consideration. So that of course can be a future scope. I think I missed mentioning that. But yes, I'd have to figure out which machine was used for the DDSM dataset and also which ones are used for the in-breast dataset. So I think when I expand this, I'll be doing a classification based on the different machines also. So they have certain differences between what kind of images come out based on the DDSM dataset and the in-breast dataset, since they were different machines. So that also will be a future scope of the study, Professor.
Okay, awesome. So let's thank Suchir again for a great presentation. So thank you very much. It was nice to hear your presentation.
Thank you so much, Professor. Thank you so much. Thank you so much for listening.